In this video, we're going to look at how to sketch tan graphs. We'll start by exploring how each term impacts the overall shape of the graph, and then we'll finish up with an example of how to sketch them by hand. For those who don't know me, my name is Chris Inazzoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. Without any transformations, the tan graph looks like this. You'll notice pretty quickly that it looks nothing like the other circular functions. The tan graph is immediately recognizable as a bunch of these cubic-like shapes that are separated by asymptotes. These asymptotes are caused by a divide by zero error, which makes itself a bit more obvious when you realize that tan is just sine divided by cos. Cos goes to 0 at plus minus pi on 2 and plus minus 3 pi on 2. And sure enough, that's the location of our asymptotes. The other thing to touch on here is that tan is still periodic, but unlike sine and cos, which typically has a period of 2 pi, the graph of tan typically has a period of pi. It's always going to be half that of its equivalent sine or cos. This is because tan is periodic with its asymptotes, which occur twice for every revolution around the unit circle, whereas sine and cos need a full revolution before repeating once. The A term is a dilation factor from the x. It's responsible for stretching the graph vertically. And all this really does is make the graph either smoother or sharper. As A gets larger, the transitions become much smoother, whereas if A gets smaller, the transitions become much sharper. The N term works similar to how it works for sine and cos. It's used in calculating the period of the circular function, although when it comes to tan specifically, its period is calculated by just pi over n rather than 2 pi over n. And once again, this is because its period is half that of an equivalent sine or cosine. In this example, we have tan of 2x, and since n is 2, the period of tan 2x must therefore be pi over 2. Okay, let's try to sketch a graph with just these key features. Well, the first step is going to be to find out where our asymptotes are, and we can always do that by finding where the cosine component is equal to 0. If you like, you can take an additional line of working to convert tan to its equivalent sine divided by cos, but that's only if you want to better see what you're doing. In any case, we're just looking for where cosine of 2x is equal to 0 over that given domain. This is just like solving a circular function. In this case, it's a composite function, so we're going to start by substituting the inner brackets and then converting our domain to an equivalent u domain. If you need to review how this works, then check the link above. Anyway, referring to the unit circle, these solutions are going to occur at plus minus pi over 2 and plus minus 3 pi over 2. All we do here is get everything back in terms of x, which just means replacing u with what it originally was, 2x, and then dividing all of our solutions by 2 to get everything back in terms of just x. Now that we have our asymptotes, we can move on to finding where the x-intercepts are. And there's actually 2 options for us here. The lack of vertical translations in this kind of graph mean that the x-intercepts will always occur at the midpoint of all of your asymptotes. So that's a perfectly valid way of finding the x-intercepts of a tan graph. If you forget about this method, then you can always use the second approach, which would just be to set y equals 0 and solve for x, just like you would for any other type of graph. This would mean that we're solving a tan circular function. So we're going to start by getting tan on its own by dividing both sides by 3. Once again, we replace the inside with u and we fix the domain. The good news is we can use the earlier working out to help us out with this. Referring to the unit circle, we can see that the solutions to this are going to occur at 0, plus minus pi, and plus minus 2 pi. All we do from here is put 2x back into that equation and then divide everything by 2 to get everything back in terms of x. So basically, if there are no vertical translations, you could do the midpoint method, otherwise you'd have to fall back on just solving a circular function. Alright, so now that we have our intercepts, we just move on to finding the endpoints. The good news here is that we actually already did find the endpoints when we solved our x-intercepts. So all we're going to do is sketch the graph for all of our key features. If you do need to find the endpoints separately, then all you would do is sub those endpoint x values into the original equation and thus get the y value at those spots. Anyway, that being said, you'll notice that all the asymptotes occur at exactly where we calculated them, and you'll notice that the x-intercepts all occur at the midpoints of all of those asymptotes. All we did from there was draw a bunch of cubic-like shapes in between each of those asymptotes. Reflections about the x-axis are signified by the negative sign out the front, whereas a reflection in the y-axis is signified by the negative sign attached to the x. You'll notice that both reflections look identical. This is because tan is considered an odd function. and it behaves pretty much identically to that of the cubic, where if you have a regular cubic, it's going to start at the bottom left, end at the top right, whereas any reflections are going to cause it to go from top left down to bottom right. Horizontal translations are determined by the h term. If you have x minus h, then you're shifting your graph to the right by h. In this example here, we have x minus pi over 2, so all of our key features are going to move to the right by pi over 2. Whereas if you had x plus h, then you'll be shifting to the left. In this example here, we have x plus pi over 3, so all of our key features are shifting left by pi over 3. If you have a horizontal translation, it's quite likely that your y-intercept will no longer occur at the origin. Under these circumstances, you might have to sub in x equals 0 to find that y-intercept like you would for any other graph. The last complication are going to be vertical translations. You can think of these as setting the y value of your inflection point. Just a quick note on that. If you've already studied calculus, you might have been told that inflection points have a gradient of 0, and that's mostly correct. But there is a nuance to that. It's only stationary points of inflection that have a gradient of 0. The point of inflection for a tan graph is not a stationary point of inflection, so trying to find that by setting gradient equals 0 is not going to go well. But anyway, that's just a tip for if you've already studied calculus. But alright, if you have plus c, then your graph is shifting up by c. In this example, we have tan x plus 1, hence the graph is shifting up by 1. And you'll notice that the point of inflection also now occurs at y equals 1. If you have minus c, then your graph is shifting down by c. In this example, we have tan x minus a half, and once again, everything is shifting down by a half. One thing to finally touch on is that the inflection point will still always happen at the midpoint of your asymptotes. That never changes. However, one issue with the vertical translations is that it means that your x-intercepts are no longer going to coincide with that midpoint. So there's just going to be an additional step where you solve those individually. First, we just want to make sure that we're starting with the general form of the circular function. That way we can very easily see what all the key features are. For this, it just means taking the coefficient of 3 off of the x. That way we can better see the horizontal translation. From here, we're just going to find our asymptotes by setting the cosine component to equal 0 and then solve for x. Once again, we start this by replacing our brackets with u and then fixing up our domain to be in terms of u. From there, we know that cos is going to be equal to 0 at pi over 2 and 3 pi over 2. So we just keep finding solutions until we fill out our domain. Having done that, we're just going to get everything back in terms of x, which means dividing everything by 3 and then subtracting pi and 3 from all of those solutions. Having achieved the asymptotes, we're now just going to find our inflection points, which is pretty quick. It's just the vertical translation of 1. Hence, all of the inflection points are going to occur at y equals 1. Now, we just want to have a look at the overall shape. We have a reflection term, which means we're going to go from top left down to bottom right, just like how the cubic would. Okay, now that we've done that, let's try the axes intercepts. Starting with the y-intercept, we're just going to sub in x equals 0. This is pretty quick to resolve. Then we can move on to the x-intercepts, which is just a matter of subbing y equals 0. Again, we're just solving a circular function, in this case for tan equals 0. So once again, since we have a composite function, we're going to replace our brackets with u and then fix up our domain in terms of u. The good news is we can borrow the results from earlier to help us out with this. Having done that, we just got to figure out where tan is equal to 1 over that given domain. And after finding those solutions, we're just going to divide everything by 3 and subtract pi and 3 from all those solutions. From here, normally we would have to find the endpoints, but in this case we've actually already found them. We know they're asymptotes. So all that's left to do now is plot the graph with all those key features. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.